It's okay?
Okay.
Thank you. So I would like to introduce the topological solitons. So you work with topology, and here we would like to give life to this topology by defining energy density Hamiltonian, and according to this energy there will be some evolution. Yes. So we start with Sine-Gordon model. Does anybody here know Sine-Gordon model? No. Oh, okay. Oh, one person. Yes. So it's very basic topological soliton model, one-dimensional, and then I will go to so it is very nice model which can be realized with lattice of pendulum. Yes. So just pendula connected with spring. Please interrupt me and we can discuss. Just pendula connected with springs, and so usually this pendula want to be down due to gravity. Yes. But there is one down, and this two pi farther there is also down. Yes, so the potential is periodic. Yes, so we can have one down here and 2 pi down, 2 pi farther here, and then we can have to infinity. This minimum vacuum it's called here, and here the second vacuum, the 2 pi farther, and here is some configuration minimizing energy. Yes, so this is one rotation. This is quantized particle. Yes, so this kind of particle in this model, it has some energy hidden in this configuration. To destroy it, you need to interact with the opposite anti-kink. Yes, so we have charge quantization kind of. Yes, so we have 2 pi times integer number rotations. We can only create them in pairs. There is some energy hidden here which can be released in this annihilation by meeting it with anti-kink, and it also has the entire special relativity. If it travels, then you get the Lorentz contraction, and also time dilation. So this is a very extremely simple model, and it recreates a lot of particle physics. Yeah? So physicists very like this model. And but we would like to go to further into particle physics. So we'd like to get to two-dimensional models. This one-dimensional. So we get this kind of topological charges, and we get interaction, like Coulomb interaction, literally. For example, in liquid crystals, they experimentally get this kind of structures with long-range interactions. And finally, we would like to get to 3D, and to find these are the final topological defects. I think it's very promising for particle physics. So from the other perspective, the main purpose we would like to satisfy here is start with repairing of electromagnetism. So electromagnetism has two weaknesses. So one weakness of the electromagnetism is the charge quantization. We have this Gauss law that integrating electric field over a closed surface, we get electric charge inside. But with Gauss law, we can be a real number. While in nature, it is integer multiplicity of the elementary charge. So we need to build in the Gauss law the charge quantization as topological. Yeah? So this is one thing we would like to repair. So we will interpret this as electric charge, this kind of topological charge. And the second problem with electromagnetism is infinite energy singularities. Yeah? So the charge has infinite energy in naive way, so we will repair it by allowing, so we have field of unitary vectors, but we allow to deform this field into something symmetric in the center to avoid the singularity of infinite energy. Yes, so we start with repairing these two problems of electromagnetism. One is charge quantization by making that Gauss law counts topological charge. So it is done by interpreting curvature of this vector field as electric field, and the second is the regularization that using field of unitary vectors of this kind of objects down to the center, there will be singularity here, and this singularity would have infinite energy. So here we can see that it is avoided by deforming this object to spherical object. Yes. Okay. So in physics, we start with the main goal is the electron, the decentral particle, the simplest particle, but also the most mysterious. Yes. So from one side, it is electric charge. That means that it has electric field, 1 over distance squares. So it's not just charge, but this is electric field. It is center of electric field. Singularity, as thinking about perfect point particle. But it is also magnetic dipole. It is also a magnetic field. This simple electron. It is also has kind of a gyroscope. What does it mean to be a gyroscope? That having this spin axis acting in this direction, it responds in this blue direction. Yes, and it has also a fourth property. It's called Zitterbewegung, the Broglie clock. That using this Schrödinger equation, Dirac equation, this is stationary. So stationary object. The question is what energy should we put here? And in relativistic quantum mechanics, we should put mc square, the mass of this particle. If you do it, then it turns out that it has a frequency approximately 10 to 21st hertz frequency. So extremely fast rotations, intrinsic rotation of this structure of electron, and it is required by relativistic quantum mechanics, Dirac equation. It is confirmed by simulation of Dirac equation, and there is a direct confirmation in this article. So how did they confirm directly this clock of electron? This 2008 article, this one. They shoot very fast electrons, ATMF electrons, and thanks to time dilation, the ticks, the distance between the ticks becomes smaller. So the distance 10 to 20 hertz is too large. So thanks to very high energy ATMF, it becomes smaller. And if getting agreement with these ticks, distance of these ticks, and the lattice of the silicon crystal here, then they get increased absorption. So kind of resonance of these ticks of the clock and the spatial lattice of silicon lattice. Yeah? So they get increased absorption, confirming the clock that there is indeed some extremely fast 10 to 20 hertz internal rotation of electrons. Yeah? So the big question is how to get all these properties for electron for one object. So assuming perfect point. So it is quite kind of naive to say that electron is a perfect point. It's also there's a field around. Both these two fields and the gyroscope and the clock. So how to get all these properties into electron? Yes. So we need some field configuration, and here is the final view. I believe is well described all these four properties. So this is a Hedgecock. So we have axis field of three axes. So we have three different axes. Yeah. So it is achieved in liquid crystals. So we have three different axes, and the longest axis makes as a Hedgecock, has topological charge. But also, doing so, the second axis, you would like to align the second axis on the sphere, and we cannot do it to this Hellebore theorem. Yes, so there is needed additional defect at the surface. So we need additional magnetic like defects here, and also we need additional this rotation, this clock. So additionally, this field should continuously be twisting. Yes, so we need also the mechanism for this twisting. So please interrupt me if there are any questions, comments. Okay, so here is some philosophical questions. So we have these fields, we have the particles, and the question is, what is the difference between fields and particles? Do we need both, or maybe particles only have some special configuration of the fields? Yes, so that was the belief that we don't need some additional points. We have only fields, and particles are just some special configuration of these fields. Yes. So and also we have electromagnetism and hydrodynamics. We have good intuition for hydrodynamics, but from a mathematical perspective, especially if we have no viscosity in superfluid, the equations are very similar. So electromagnetism and hydrodynamics are quite close mathematically. Yes. The main difference is the speed. Still speed of light, still speed of sound. Could we take this similarity between electromagnetism and hydrodynamics closer? Yes. So that's the big question here. Yes, and in liquid crystals, as mentioned, this particle similarity is taken much further. They literally get these topological charges, this kind of topological configurations, and they look, for example, at the positions of such two topological charges. So here is some distance versus time, and it turns out that indeed this distance is reduced, and then they can check with what kind of long-range interaction it agrees with. And it turns out they get some 1/distance interaction Coulomb-like interaction, dipole-dipole, so they can get with these topological objects. So literally they have some molecules which are elongated molecules in these liquid crystals, and they have topological structures like this hedgehog, and looking at position of these two topological structures in these liquid crystals, they can look at distance, and they get what kind of log-managed interactions. So they can get particles in these liquid crystals. So the question is how far we can take it further, this similarity with particle physics. Yes. And so here is the simplest model, the Sine-Gordon model. Yes. So as mentioned, it is it can be realized with just a lattice of pendulum. Yes. So we have this pendulum. They connected with spring. So they prefer to have the similar angle. Yes. And also there is the gravity. So we have two terms. So we have so finally the equation, simplified equation is this second time derivative minus second position derivative equals this potential. So sine is the potential that they want to be down, but there is down every 2 pi. Yeah? So this is another down. So it can this energy minima are called vacuum in liquid crystals. So it wants to be down, but by the solution it can go here, and we can see that there is some energy hidden in this configuration. And to release this energy, we like to meet it with antiparticle, yes, anti-kink. So here is some scenario that we have two. We have this. So here is the angle, yes. So we have one kink here. So here is this one particle, and here it meets with antiparticle. Yes. So now they are massive, so they contain energy inside. Yes. So then are traveling, and now they cannot exceed the maximal speed, the propagation speed, the speed of sound here. Yes. So if reaching this speed of sound at maximal velocity, like here, we have this Lorentz contraction. So here is standing, and here is moving, and we can see that it's much narrower. Yes, so it's literally as special relativity Lorentz contraction. So when they meet with having finite velocity, they can release this energy hidden in this potential and the springs, and now they radiate with massless radiation. Let me find the animation. Okay, so here is some animation. Yeah, so we have this particle, this kink, anti-kink. They are traveling with finite velocity below this maximal propagation speed. Now they meet in the annihilate. Yes, they release this hidden energy, this mc square, this Einstein mc square. Yes, and now they release it as a massless radiation. Yes. Okay, so here is the equation governing this system simplified. We can calculate the energy of given configuration given by this formula. So it has both this stress of this. So here is the stress of the springs, and here is energy of stress of the springs, and here is the energy of this kinetic movement. Yes, and plus the potential energy from the gravity. Yes. So having this kind of configuration, minimizing energy as this integral, this energy is finally released when they meet. Okay, so it is a very simple model which creates the varying number of particles. We have finite velocity. Then when we have pair creation, annihilation, quantization of this charge as this number of full rotations, and a tiny special relativity. Okay, so here these were for one-dimensional topological defects, and in 2-3 dimensions there are very popular these vortices. So both in superfluid and superconductors. For example, superfluid, a fluid without viscosity, turns out that when they rotate it, they have interior number of this kind of fluxes. So they literally there is angular momentum quantization. Yeah. So each such vortex contains one quant of angular momentum. Yes, so if you make it faster, then integer number of vortices will be added. So here is for we have angular momentum quantization in liquid crystal in superfluid, and through this analogy between superfluids and superconductors, we have also a quantization of magnetic field in superconductor. Also, so if you put a magnetic field, then the number of these, so we have these fluxes, each has one quant of magnetic flux. And why it is quantized? Because there is some as in this argument principle, that there is some phase, it calls other parameter in physics, and looking at the loop around of rotation of this phase, it has to be 2 pi times some integer number. Yeah, so we can take a loop and we can calculate how many times this phase rotates. It has to be integer multiplicity of 2 pi, and they define what happens inside. So they define sum of charges inside. So if it's +1, so if you go around, there is +1 topological charge. So here is +1, -1. So it could be just +1, but it could be also +1, and -1. So these boundary conditions define as a sum of quantized charges inside. Yes, so here is +1, here is -1, because the field, if you're going around, the field rotates -1 times. Here it rotates twice, the field rotates twice going around. It rotates 3 times going around. Yes, so we have for superconductor or superfluid, it will have 3 quants of this angular momentum or magnetic field. Please interrupt me, or if there is there are some comments. Okay, so we have in 3 dimensions. We work in that we have 2 types of topological charges here. Yes, so we have 2-dimensional topological charges that take a loop around. We calculate how many times the field rotates. It has to be integer number times 2 pi. Yes, so here is +1 charge. Here is also +1 charge. The difference between this and this is that we rotate all the angles by the same angle. So in physics, it's called Gaussian invariance. That only the relative phases are important, not the absolute phases. Here is -1. Here is +2. But we can also have 1/2. So let's see that we have 1/2 here. That indeed rotating this field around, it rotates by -1/2. Yes, so the field rotates going around this kind of this topological defect. The field rotates from this to this. Yes, but using field for which it is the same. If you field of ellipses, this ellipse and this ellipse is the same. Yes, so having field with symmetry, here is Z2 symmetry, then we can have these fractional charges like 1/2. Yes, that rotating at this. And this is the same, then we can have -1/2, and indeed in liquid crystals they observe this kind of fractional charges, fractional topological charges. And in physics we have 1/2 for spin. Yes, so in physics there is for example this quantum rotation operator that rotating spin S particle by theta angle, the phase rotates by S times theta. And this is exactly what happens here. Yes, so we can interpret it as spin, this topological charge. Yes, because rotating this picture by theta angle, the angles will rotate by S times theta. Yes, where S is this charge. So these two-dimensional topological charges are similar to spin. Why to get charge, we need to go to three-dimensional topological charges, like this hedgehog. Yes. So here, these are kind of spin-like, and this is electric charge-like, and we can have this long-range interaction that we have. We can have plus, minus in various distances, and visually we can see that the stress of the field is larger here. Yes, so here is more calm field. We formalize it further. And here is more stress. So to minimize the energy, we'd like to make them closer. So we get Coulomb attraction thanks of this energy minimization to reduce stress of the field. Yes. Okay, so here are the topological versions of electromagnetism. So for electromagnetism we have the Gauss law that is integrating electric field over some closed surface. We get the electric charge inside, but it has it can be any real number. While in physics it should be an integer multiplicity of the elementary charge. And we have this Gauss-Bonnet analogy, which also interprets curvature this time of some let's say vector field. So it's very similar, but instead of electric field we use curvature here. Yes, and using that we have the charge quantized Gauss law. Yes, so it integrates the topological charge inside. So we can repair the lack of charge quantization in electromagnetism if interpreting curvature of some deeper field as electric field. So that's the main point by Magnus Faber I'm collaborating with. And we recreate electromagnetism, but using Gauss law as the Gauss-Bonnet theorem to have built-in charge quantization as topological. Yes, so we have the Christoffel, the connection, which says, so we have let's say field of unitary vectors U. We have the connection, we have the curvature, and we interpret this curvature as electric field. And finally, we have this, in electromagnetics, we have this Lagrangian, where this is F tensors. And here we use, instead of F tensor, we use the R tensor, the curvatures. So interpreting, we interpret the curvature of some deeper field, like a vector field, as F tensor, dual F tensor. So it's, and use standard Lagrangian of electromagnetism, and this way we create electromagnetism for these topological defects. Yes, so we get electromagnetism with built-in charge quantization as the Gauss law counts topological charge of some deeper field. Okay, so here is some approximated calculation of Coulomb interaction. Yes, so we have these topological charges. Here are the opposite charges in various distances. Here are the same charges in various distances, and we calculate the energy of such configuration by integrating this energy density, this Hamiltonian. Yes, so we have this configuration. Now it's given by ansatz. Finally, it should be optimized, and we integrate this energy density for each such configuration, and we get these points. So the points are here is for the opposite charges. So the points are from the integration of energy density, and the line is from fitting 1 over R, like in Coulomb. You can see that indeed it's very close to Coulomb interaction. Yes, so looking at energy of this kind of configuration of two opposite charges, which are now quantized due to topology, this energy is indeed reduced when we're taking these opposite charges closer, exactly as in Coulomb law. Yes, so we get effectively Coulomb interaction for these topological charges. Coulomb attraction, and for the same Coulomb repulsion. Yes, so we have these topological objects with built-in charge quantization as topological, and we're looking at the effective behavior, they get Coulomb interaction. So there are some approximations here. One is that I use this ansatz. It should be optimized, this fit configuration, assuming the constraints, topological constraints. The second approximation is that there is a cutoff in the singularities. So if I wouldn't use this cutoff in the integration, then it would be infinite energy. So later it will be regularized by, I mentioned a moment, but here there is just cutoff. So it has to be repaired finally. Okay, so another question is what about quantum mechanics? Do these kind of topological objects behave according to the quantum mechanics? And there are many articles like this. For example, for these fluxons, these topological objects in liquid in a superfluid superconductor, there is observed interference, tunneling, Aharonov-Bohm effect. Then there are many quantum-like effects for very nice bouncing droplets experiments. They have this liquid surface, and it's shaking, and there is a droplet, and this droplet gets coupled waves, and these waves act as this pilot wave, and indeed they get interference in the double slit experiment. So there are single droplets, but when they calculate statistics, they get the interference patterns as in quantum mechanics. More interestingly, they get the orbit quantization. But the droplet makes an orbit, but these are not any real radius, but integer radius. So here is one orbit, and here is another orbit. So why it's quantized? Because the coupled wave made by this bouncing has to become a standing wave, as in Schrödinger equation. So there is a resonance conditions which leads to the quantization of the orbits. And here, for example, they get a double quantization, both of the radius of the orbits and of the angular momentum of the orbits. So very nice experiments recreating of quantum effects for point-like objects coupled with waves. So the question is, when is this boundary between classical and quantum physics? And maybe this is not boundary, but rather two different perspectives on the same system that we can think about them classically or from quantum perspective. For example, having coupled oscillators, we can describe them classically, kind of, and or going to these normal modes when you have unitary evolution in this normal mode. So this is kind of classical perspective and quantum perspective on the same system. Then you have crystals. You can describe them classically or through the normal modes, Fourier transform with phonons, and again going to the normal modes. Then there is continuous limit, and they can recreate a lot of quantum-like effects here. And finally, we have the most difficult situation where there is a varying number of particles. Yes, there is also this per creation, per annihilation. And usually it is done by perturbative quantum field theory, but you can also do it with this topological solitons model, that you have also the varying number of particles. You can have pair creation, transform energy, you can create pair of opposite charges. Okay, so here are the final models I'd like to go to. Maybe let me. So now it was introduction. Now I will go to this more slowly to these models. Are there any questions, comments? Okay, so once again, this is a Sine-Gordon model. So we have the equations, the partial differential equation with the potential, this gravitational potential. So here is a resting one, here is a moving one. You can see the Lorentz contraction, but it is wide, this is not narrow. Okay, so we can have energy density. And so here are some calculation. We derived this shape of, so in this model, Sine-Gordon, it can be derived analytically, the shape of this one kink. So it is done we assume this form, and we can get this kind of shape, depending both of position and velocity for traveling, and calculating energy of this shape, mass, momentum. It scales as in special relativity. So we literally recreate the special relativity with these models. We get also the time dilation that having a clock, and when this clock is moving, it slows down. Yes. So here is these are called bleeders. Here is position. Here is time. So here we have some oscillation, and now here is standing bleeder, and here is now it is moving. And we can see that the number of ticks is smaller. Yes, so they have time dilation literally. So for a moving particle, it slows down. Its internal processes are slowed down. Like for electron, I mentioned that to observe this clock of electron, they have to use very fast electrons, like ATMF electrons. Okay, so the Lorentz contraction. Some interaction I have mentioned. Okay, so and now for higher dimensional topological solitons, and there are these mainstream Skrimian models. So for example, there is a group in Krakow, Andrzej Werszczyński, Tomasz Czukiewicz, Nick Manton, a lot of people. They try to recreate nuclei, atomic nuclei with these kind of solitons. What is however, they only get short interactions in these models because they use potential which has minimum only single minimum. So far from particle, this field goes to this single minimum, so they can get only short interaction, usually exponential weakening of the interaction. Also they interpret topological charge as the baryon number. So the baryon number cannot be evaluated in these models. So that's the big question: can it be evaluated or not? And for example, it is assumed to be evaluated in baryogenesis and Hawking radiation. So in baryogenesis, there was this big bang, and finally we see that it's more matter than antimatter. And the question is, in theory, it validates the baryon number, unless there was the same baryon number before the big bang. But so in theory, it validates baryon number. Also, this Hawking radiation. So this is we take baryons, beat a star, wait until it collapses to black hole, and then it radiates its massive radiation. So this way it destroys baryons. Yes? So again, in theory, it validates the Hawking radiation. So that's the big question. Should we interpret topological charges, 3D topological charges, as the baryon number here, or maybe as electric charge? What we do with Manfred Faber and some liquid crystal people. So to get long-range interactions, here there was only short interaction, we use Higgs-like potential. Yes, so we use this potential which has minimum, for example, on a sphere. Yes, so there is this potential which prefers, let's say, unitary vectors here. So the field wants to be unitary. However, sometimes it would need to have infinite energy, then it deforms, let's say, to zero in regularization, I mentioned in a moment. So thanks to long-range interactions, we will get these electromagnetism, for example, and there are other long-range interactions. For example, in liquid crystals, they also can also have this non-trivial vacuum because this is the shape of the molecule they are using. It's not spherical molecule, but elongated molecules. Yes. Okay, so now let's think about this simplest two-dimensional system. Yeah? So we fix Higgs potential. So we have a vector field which we fix potential. So it prefers to be unitary vectors. However, having this hedgehog, if having unitary vectors down to the center, there would be discontinuity in the center. Yeah? So it has infinite energy if using only unitary vectors. So what can happen? So here you can see that these unitary vectors, preferred unitary vectors, were deformed into zero vector in the center to avoid the singularity. Yes, so the potential prefers unitary vectors. However, sometimes there are allowed deformations to avoid infinities. Yes, so far from practice we have electromagnetism. However, very close to these singularities we have other interactions weak strong in physics. Yes, so that's the intuition here. So we have some energy both from the temporal and spatial derivatives and this Higgs potential. So we can find the optimal minimizing energy field configuration. So we need to find the radius. So we found Higgs potential. We would have radius equal 1, and the energy would be this green line going to infinity. So it would integrate to infinity, so it would have infinite energy. But it is avoided by deforming the radii down to zero in the center. And this way, we activate two other types of energy. So one is the potential, the orange one, and the second is the associated with the derivative in the radius direction. Yes, so we found Higgs potential, the green line would go to infinity, the energy of this charge would be infinite, but to avoid it, we activate the orange, the potential. It allows us to get finite energy. And finally, this energy should be energy of the particle, which is the mass So for electron, it should be 511 kiloelectron volts. So we know what it should be, and literally in this model we try to get the proper mass of the particle, which will be released in annihilation of this particle when meeting with antiparticle. Okay, so some simple model of interaction, but okay, so we can get some. Again, having the opposite charges, integrating the energy density, we can see that visually the stress is lower here, so the field wants to go here, and we can find this energy and treat it as some effective potential, like Coulomb potential. So here is once again this Coulomb potential. Yeah, so we have these configurations of two topological charges in various distances. We integrate the energy density, and then we get an effective Coulomb-like potential. Yes. Okay, so the question is about this finite size effect. Yeah. So it is electronic here. The charge is not a perfect point. It has this deformation. So this deformation is required because here is the energy density of electric field around perfect point charge. So if we integrate it from 0, then it would be infinite energy. So that is problem that perfect point would have infinite energy. And to avoid it, we know that electron should have this mass of electron should have this energy. So not to exceed this mass of electron with energy of electric field alone, we see that we need to deform it in a femtometer distance. Yeah. So we need deformation in femtometer distance, and here this deformation is by changing this length of these vectors due to Higgs potential, and it turns out it leads to some deformation of Coulomb interaction. So for very short distances, that means very high energy, then the Coulomb interaction is slightly deformed. So here are numerical values. So the solid line is the Coulomb interaction, and here are the numerical values. So you can see that there is slightly stronger interaction in very short distances. So due to this deformation, which is required not to exceed mass of electron with energy of its electric field alone. Yes. So and it turns out that it agrees with the so-called running coupling effect. That indeed for very high energies, the alpha, which controls the strength of Coulomb potential Coulomb force, is deformed. So it's slightly Coulomb interaction is slightly stronger for very high energies. What you can see that the potential is slightly steeper for very low distances. So this deformation, not to exceed mass of electron with energy of electric field alone, leads to Coulomb-like to running coupling, deformation of Coulomb interaction in agreement with experimental data. So here the electron is perfect point, but there is some deformation of electric field very close to the center of its center, not to exceed 511 keV with energy of electric field alone. Okay, so I have some about experimental experiments about size of electron. So there is some. If asking physicists if electron is perfect, they usually say that it's a perfect point. So one reason is that because in perturbative quantum field theory they cannot work with non-perfect points because it's extremely difficult from mathematical perspective, experimental reasons. So one is Delmel's argument based on the so-called G factor of electron. So what did Delmet do? So Delmet drawn this plot in his article 1988 or 9. So we have 2 points. Triton as made of 3 nucleons, proton as made of 3 quarks, and assuming some hypothesis that electron is also made of some 3 partons. So here is the G factor, here is the size. So from 2 points, he wanted to extrapolate to the 3rd point. So if he would use a straight line, he would get negative radius for electron. So he has used a parabola. So he had extrapolated from 2 points with parabola. So we know that he cannot do it, but it is the main argument people use. This plot, which makes completely no sense. So if you look at this argument, it makes no sense. So a better argument is the scattering. They smash electrons and positrons with very high energies, and what they see, so here is energy, logarithmic scale, very high energy, Here is this cross section, so the area of this smashing. So what you can see that there are some resonances corresponding to particles, but there is also this straight line. So these are extremely high energies, but while we are interested in size of resting electron. So we should extrapolate this straight line to energy of resting electron plus positron. If you do it, we again get this 2 femtometer distance, some deformation required. Or another argument is that if electron is a perfect point, then we would need no running coupling. This deformation is very long distance, which is observed experimentally and is obtained if deforming the electric field not to exceed mass of electron with electric field alone. The reflective field alone. Okay, so here is the two-dimensional argument principle, probably well known. Equations. Okay, some interpretation of the field, of electric field. The F tensor. So physicists work with these F tensors, which has electric and magnetic fields. 4x4. But we in fact interpret the curvature as F dual. Dual means that we exchange electric and magnetic field. So there is duality between electricism and magnetism. And after this duality, mathematically is very similar. However, there are some small differences, like we don't observe magnetic monopoles, but we observe electric monopoles, charges. Yes, we observe fundamental magnetic dipoles, but not electric dipoles. And so, if interpreting this curvature as standard F, you would get electric monopoles, these Dirac monopoles, and magnetic monopoles and electric dipoles. So what is the main trick of Faber? That we use the dual formulation, that we interpret the curvature as this F with exchange magnetic and electric fields. This way we get electric monopoles, that means charges, and magnetic dipoles as it should be. Okay, so again, here is this numerical Coulomb interaction and running coupling. So you can see that there is some deformation. So it's slightly stronger for very low distances. And running coupling indeed for very high energies. The alpha which decides that the strength of Coulomb interaction is larger. And having Coulomb interaction in Lorentz invariant theories, we get entire electromagnetism. This is also well known. So this way we will get the entire electromagnetism. Okay, so this one once again this early picture that indeed we get these topological charges, but we also need this magnetic dipole moment and the gyroscope and the clock. The question is how to get it. So I think this is the way to get. So we get topological charge of this long axis, but we have also this twisting of the short axis. The question is what prepares it. Okay, so finally, so I have started with this kind of topological charges in 3D, for which we can get electromagnetism by using Hamiltonian electromagnetism, interpreting curvature as F tensor. And now we get one type of charge, but as electron interpreted. But in physics we have three leptons, which are very similar. We have the same electric charge here as topological, but different mass. So here is some a way to get them. To distinguish the three axes. This way we can get the topological charge, the hedgehog, with one of the three axes. So you get three types of realization, which asymptotically give the same electric charge. We have the same electric charge, but have different realization, different mass. So this way you have three leptons because of living in 3 dimensions. Yes. And we need to understand this kind of hedgehog, which additionally, due to Harry-Boyle theorem, requires these additional topological defects because we cannot align the vector field on the sphere. Yes. So here is some view for further particles. Yeah, so having this, so this field, looking at topological excitations of this field, a field of three different axes, which are experimentally realized in liquid crystals. These are called biaxial nematics. There's molecules, elongated molecules, but also recognizing the twist of this molecule. Yes. So let's look at the topological excitation of this field and try to see if there is resemblance with particle physics. Yes. So here is this basic charge. Having three axes, we can have Hedgehog of one of the three axes, so we get asymptotically the same topological charge as electric charge, but different realization of mass, so as electric leptons. Also due to this Herible theorem that if you cannot align the second axis, we also need magnetic dipole moment. So we don't have naked charges, only they need to have magnetic dipole moments also. Then we can have this kind of vortices, yes, so simple knots as you like here, yes. So in cross section there is this two-dimensional charge. Here is 1/2, and so again you have three types of this kind of let's say torus scheme. So from physics perspective, they should be very light, very stable, and what more, we could rotate continuously between them. Yes, so we just continuous rotations. We can go between them, and it is known in physics that we have neutrinos, and they can oscillate between different types of neutrino. They resemble three neutrinos, which can oscillate between these kind of structures. But much more interesting are the simplest knots in this view. So we can have this knot that we have this this vortex fluxon with this kind of cross section, and a second around. Yes, also this kind of structure. So taking a cross section here is the central vortex. Here is the second one around. So you can see that this loop around deforms the field inside. This loop around deforms the field inside into a hedgehog. And hedgehog is electric charge for us. Yes. So this way, baryons require some electric charge. Having this remark that baryons enforce themselves some electric charge, we can explain why proton is lighter than neutron. Because in proton we can just enclose this hedgehog enforced by this loop around. In neutron we have positive charge, but it has to be compensated from both sides to get zero finally. Yeah, so and this compensation costs energy. So it can explain why neutron is heavier, because it needs this compensation, which is heavy, and it agrees with the charge distribution of neutron. So here are some charge distributions for proton is positive, but for neutron it should be positive core and negative shell. This is exactly what we can see: the positive core and negative shell for neutron. So this simple model, looking at excitations, topological excitation of this simple model, we get very nice similarity with particle physics, basics of nuclear physics. Then we can go to nuclei. So we could take such two baryons and take them together. And what we can see that both require some charge. So they enforce some part of hedgehog, and so here is some minus to compensate. So if both they require the charge, so now they want to bind together to satisfy this requirement of charge. Yes? So it would give them the mechanism for binding of baryons into nuclei, because they require some charge. So here we have some simple mechanisms for binding. And also we can have more complex knots for larger nuclei. That we have this vortex, and it can form a larger. So this way you can view nuclei as knots. So I think it should be the most interesting for you. So here is, for example, four baryons. This is very stable nuclei, and also there are no topological, and there are no nuclei. There are halonuclei, that we have the nucleus, but also a few two neutrons, for example, two protons, single protons in very large distance, so larger than of strong force, and stay stably binded to two neutrons here, for example. So the question is, what could stably bind them in this very large distance? And again, this vortex, there are many articles hypothesizing these one-dimensional structures in physics. So a very nice argument is this corona of suns. So looking at the corona of sun, they see these shining one-dimensional structures. They are very stable. And so the question is why they are stable. So maybe this is topological reason. And there are hypothesized these cosmic strings, again, one-dimensional defects of this argument making 2 pi around this vortex. So there are arguments that indeed there are these one-dimensional structures which could, for example, allow us to see nuclei as knots. So it needs to be analyzed. And okay, so here are some other arguments that predictions of these very simple models, suggestions of these very simple models agree with particle physics. So I have mentioned that neutron indeed has positive core, negative shell. What is predicted here, that this positive core is required by its interaction with this external loop. A negative shell is that finally we have quantized charges. So finally we have Gauss law. So in large distance we have Gauss law, but locally these full topological charges can be deformed, like enforced by this interaction with this loop around. Then for the deuteron, the simplest non-trivial nucleus, as just proton neutron. So here is the configuration. So from charge perspective, it's plus minus plus. So it means electric quadrupole moment. And we know well that it is well known that the deuteron has quadrupole moment. So it's very non-trivial. If you think about proton neutron, it shouldn't have quadrupole moment. But it has experimentally, and here is the suggestion, because both require some charge leading to this plus minus plus charge configuration, which is electric quadrupole moment. Okay, so here are some arguments that it seems that there are one-dimensional structures in physics. Okay, so further, we can try to go to 4 dimensions. So in 4 dimensions, there is this gravity electromagnetism. So the question is, what is gravity? So there is a very good approximation which is called gravity electromagnetism. So if you use just Newton force, and then there is the basic problem is that it's not Lorentz invariant. To make Newton force Lorentz invariant, we need to add, for making Coulomb force Lorentz invariant, we add magnetism. Here we also add magnetism. It's called gravitomagnetism. So finally, we get two sets of Maxwell equations. One is for electromagnetism, and second is for gravity. The main difference is this change of sign, that two masses attract, not repel, like for electric charges, yes. That's the big difference. And size of this constant. And this electromagnetism is what was confirmed, for example, by the gravity probe experiment. So these are the first order, but the only one we have directly confirmed, not through some extremely far, some collapses, but through this gyroscope precession. So extremely well confirmed, and this was exactly this gravity electromagnetism. So that's the big open question: how to unify electromagnetism with gravity. So it is extremely difficult, but if we think about gravity as a second set of Maxwell equations, it seems much simpler. Yes. So and in this model I'm talking about, so we have this first vectors, unitary vectors. For unitary vectors, from these plane rotations, we get electromagnetism with charge quantization. Then we add the twist, and turns out the twist leads to some low energy Klein-Gordon equation for quantum phase. So this is kind of adding quantum mechanics, this twisting. And finally, if we go to the SO13, that means also adding boosts in special relativity. With this 3 boost, we also get a second set of Maxwell equations for gravity. So this way, we naturally unify these both equations. So these for spatial rotations, quantum mechanics from twists, and for Brown boosts, the gravity. So here are some finally some Lagrangian I'm considering. Yes, so Lagrangian is very similar to electromagnetism, F mini, but using F as interpreted as curvature of some deeper field. Yes, so for charge quantization. If we interpret F as curvature of some deeper field, then the Gauss law becomes the Gauss-Bonnet theorem, and we count the topological charge, so we're getting built-in charge quantization. And the curvature, the final curvature is has four indexes, not just two. Yeah, so using 4 indexes, turns out that we get much more. So this using full 4 index F here, we get unification with the remaining, the Maxwell equation for the gravity and Klein-Gordon for the twists, low energy. Yeah, so finally we have electromagnetism in QED, we have electromagnetism plus low energy term for this quantum phase. And here literally we have for the long axis evolution we get electromagnetism plus for the twist we have low energy contributions for the quantum phase evolution, and for the boost we get second set of Maxwell equations for the gravity. So here is this F mini calculated, which becomes here F mini becomes a matrix, 4x4 matrix, and this term, this curvature leads to electromagnetism. This term leads to quantum mechanics, and this term leads to gravity from these boosts. It's very simple unification of the Maxwell equations for electromagnetism and for gravity. Okay, so I think I have finished because I was expecting some interaction. So we have some.
We can make some break if you want.
Sure. So maybe
you're the boss. So we do. Oh.
Sure. So maybe let's make some break, and there will be some. Okay, thanks.
Okay, so let's have 50 minutes.
Thank you.